Hi, welcome everyone. Welcome everyone. So today I'm going to talk a little bit more about some of the inputs. Okay, the inputs that we are doing. Now, before I continue, I'm going to use I'm going to talk about the code that I'm going to use for analysis. So last video I was talking about the fact that sometimes when you have a sine wave. You have a sine wave input, it is really too slow. Okay, it's really too slow. For example, if you want a input for 0.001 hertz, okay, 15, okay, this is my offset, this is my oscillation amplitude, and if the oscillation, the frequency is so low, okay, at 0.001 hertz or 1 times 10 to the minus 3. One oscillation takes about 1000 seconds, and if you want to do frequency response, that's going to take some time, especially for low frequencies. So even for oscillations of 1 times 10 to the minus 2 hertz, you're still going to need to take about maybe 1000 seconds before everything settles down, and then you can really start doing a frequency response. Okay, so the way around that was to sort of superimpose many waves into this as your input instead of just a clean sinusoidal wave. Okay, that only works provided your frequencies are, your what do you call that? Your frequency response is sort of linear. Your systems are linear. That means one sine wave input produces a sine wave output. Okay, so you can see here this input here, the fuel input, this sine wave input will produce this output, which is the temperature versus time. A sine wave will produce a sine wave input will produce a sine wave output with a phase shift and an amplitude change. That's all. If there are additional frequency changes, then the system is considered non-linear. So what does that look like? Okay, so if you were to take a look at this piece of data which I have here, I use my in-house Matlab frequency response tool, which I developed. There are a few YouTube videos on that. You can check out the video playlist. Okay, so what this looks like is this. The blue colored fast Fourier transform is the input, and the orange colored fast Fourier transform is the output. So normally, so this is your magnitude plot. So this is the input frequency, and you can see this is the strongest signal among all of them. Okay, this is the strongest signal. Okay, so the blue curve and the orange curve has this strong, very, very strong signal. I did not use log plots, okay, for the reason that you can see, so that you can see that the signal here is the strongest. Okay, this blue colored signal and the orange colored signal both show a very strong peak at 2 times 10 to the minus 3 hertz. However, you can see over here there are like the so-called, maybe you might call them harmonics or what, higher frequencies. These are not the same frequency as, let's say, your input sine wave. Okay, so maybe there is some degree of non-linearity. Okay, but they are relatively small, and you can see the relative order of magnitude. This is like 10 times smaller, easily 10 times smaller than your main frequency. Okay, so if you can ignore most of these, then it's still fine. Okay, it's still fine. If this is on the level of background noise, you can just ignore that for the most part. Okay, but yeah, let's see. Yeah, so let me see the peak data. Yeah, there's only one input and one output peak. Yeah, so basically I set my threshold. Okay, if you saw my Matlab videos, I set my threshold such that only the main peak will be discovered over here. Okay, only the main peak will be discovered, which is this main one. Let's see. Peak data, yeah. So these are the only main peaks that are discovered. The rest, you don't really have them. Okay, so yeah, this is what non-linearity may look like. There's a shift in the frequency of the output. Okay, now if this were not the case, or for the most part if your non-linearities are small enough, you can actually have several sine waves being put in at once. Okay, so this will be usually in different waveforms, for example square wave or a sawtooth or what have you. Okay, and so it's not just a clean sine wave like what you're seeing here. So instead of just putting in one sine wave, you might put in multiple sine wave, you might put in a square wave, you might put in triangular waves. So of course if you were to have a sine wave as your input, so this blue color is again your input. If you were to have a sine wave as your input, then you will have this one peak here. But if you were to put in multiple sine wave as your input, then you can actually have multiple inputs here, and you can actually see, at least for these strong signals, if your response is mostly linear, then you'll have one input peak resulting in one output peak at the same frequency. Okay, yeah, you can do this over multiple frequencies in the same test, and that's going to be a lot easier on you. Okay, if you do something like that. All right, so so that's what we might want to try to do. Okay, that's what we will want to do. Okay, so how are we supposed to do this? Okay, so yeah, first off, we might want to actually compare between the between, let's say, we want to compare between, let's say, a square wave, a combination of sine waves, and maybe a sawtooth wavelength, sawtooth waveform. Okay, and ideally we will want to have, okay, if we are doing frequency response, we will be having many inputs over several frequencies. Okay, so let's put this here. So normally if let's say this is your input wave, okay, if you have one sine wave at a time, then you have one strong peak here, just like what we are doing. That's the normal thing. Okay, but let's say if you want to do multiple sine waves, so maybe instead of having 1 times 10 to the minus 3 hertz, maybe you have one at 2 times 10 to the minus 3 hertz. Alright, and then one at 3 times 10 to the minus 3 hertz. Okay, so this is called a multi sine wave. Okay, multi sine wave, or what do you call that? A summation of sine waves. Okay, summation of sines. Okay, so we'll have multiple sine waves being put in at the same time. If the response is more or less linear, so I will use a red color for response. If your response is more or less linear, then you will have this sort of diagram. Okay, this red color may be more or less than the green color curve depending on the gain. Of course, you may have some non-linearities as you saw just now, which may have this harmonic pattern. But if you can just ignore this and you can classify this as noise, then that won't be a problem. So if you have two frequencies now, okay, maybe you have this curve here. Maybe you have some non-linearities here as well. But if your noise is negligible, we can just take the ratio of these peaks to be our gain, and then of course we can look at the phase gain as well. This is a very good method if your system is indeed linear time invariant. If not, you might want to still use your clean sine wave input, but the price of that you need to pay is that it will take much longer. Okay, and of course some of these non-linearities may end up giving these these frequencies a little bit more gain depending. Okay, they may, but okay, so if that's tolerable, so be it. But if not, it's still best to use one sine wave at a time. Okay, so that's the drift I'm trying to go for here. Okay, so again, I don't know what the response of the input and output for this LabView system is, but let's check it out. Okay, I already have, I believe, some test data which I can just put into a let's put it into a CSV. Use LibreOffice, or maybe I'll just open. We'll have the 0.01 Hertz. Okay, we'll open this up with LibreOffice Calc. Okay, again, it's very nicely put in, and I want to save it as a CSV. Okay, 0.0, oh, maybe I put 1e minus 3, 1e minus 3, oh, 1e minus 2 Hertz. Okay, so we'll just put it on my desktop. Excuse me. You just put it on my desktop, and we'll just call it a 1e minus 2 Hertz data. Okay. Okay, I don't have that. Save again. No. Let me try again. Save as. E minus 2 Hertz. Use CSV format. Okay, so this is 1e minus 2 Hertz.csv, and what I will do is, of course, there's the so-called input data, which is here. This is my input data. This is my time column, and you can see I tested it for 1000 seconds going up and down. And let's check out this other one, which is the output signal. And again, I will just open it with LibreOffice Calc. I'll just copy and paste all of this, and let me paste it here. Okay, so I will try to take data that's only like after like what, 500 seconds, or maybe 200 seconds. I can't really tell which is stable. Oh, since you're LibreOffice, might as well just plot the chart. Alright, let's insert a chart. XY plot, and you. Alright, so anywhere from maybe 100 seconds onwards, because you see this frequency response plot. Ooh, yeah, this frequency response plot, things start sort of stabilize maybe after 100 or 200 seconds. So it's about 200 seconds just to be safe. Yeah, maybe you'll see here 200 seconds. Okay, so we'll just take data after 200 seconds because we see this very nice sinusoidal input. Okay, so we'll just put that through our, put it through the Fourier transform. Okay, anything before 200 seconds I'm not taking. Okay, and then I will delete rows and I'll save. And then let's put this in our Matlab. Okay, so let's put it here, and we'll put it through the Matlab. I already showed you, I mean, in my other videos I show you how this code works, but it's basically a Fourier transform. And you can see here, okay, you can see here the frequency response is as such. There is it looks very linear, okay, even though the system is inherently non-linear. Okay, I mean, you see these parts, there are other frequencies as well, probably in there. and of course I subtracted out the DC gain. But this is our oscillation of the input, and you look at the output, the amplitude here is about 6 in those so-called dimensionless units, and this 6 degrees C. Okay, now of course there are look at this, there are other frequencies over there, but that's okay. This looks more or less like a linear system. Okay, so now let's try a few different wave inputs and see what happens. Okay, I'm going to test this of course for other frequencies. Okay, so I'm going to rename this as this. I'm just going to call this 1 times 10 to the minus 2 hertz sine wave. Okay, I'm going to do the same, but let's try square wave. We're going to try a square wave. Let's try a square wave. Okay. Now of course we can try all the waveforms, of course. We'll try the square wave first. Okay, 1 e minus 2 hertz, 15 baseline power, a heater oscillation amplitude of 2. Okay, so I'm just going to have that. Alright, so as you can see, it takes a while. Maybe it takes about 100 seconds. Yeah. And while that is going on, I mean, it's going to take some time, right? Yeah. Let's see. Yeah, while that takes some time to simulate, we can, in the meantime, think of other things we want to do. Okay, so besides sine wave waveforms, okay, we of course discuss square waves, which are pretty close approximation of sine wave. We can look at the Fourier transform of that and see what that looks like. There's sawtooth. Okay, there's random. Okay, this is sine. Random, square, sawtooth. Okay, next we can try summation. Okay, so that means we will add some sine waves together, some sawtooth, some square waves together, some sawtooth wavelengths to get waveforms together. Well, random, you don't really need to do any summation. Okay, it's kind of redundant. Okay, so let's start making a summation waveform. Yeah. Okay, let's make a summation waveform VI. So I'm going to make a new subsystem. So from LabView, go to new, and then under other files. Okay, there are lots of VIs you can make, but simulation subsystem will be in other files. Just click OK, and we'll make this new simulation subsystem, and then we'll save it as not in the desktop, but we'll do oopsie, wrong one. Oops. Back. Yeah, we go to yeah, where is this? Should this be in freq? Yeah, this is a LabView thing. So let's do more LabView. LabView, yeah. Control systems. Frequency response testing. I'll make a new folder. New directory. What do we call this? We can call this directory maybe dependencies, and then we'll put the subsystem here, and this will be summation signals. Okay, so what are we going to do here? Basically, it does what it says. Okay, so I'm going to have the same inputs here. I need a oscillation amplitude, I need a frequency, and I need a power, an offset. Okay, so let's do those things. Okay, I'm going to let's see. I'm gonna yeah, this one doesn't need the simulation loop because this whole thing is a subsystem. Okay, I kind of explained this in other videos how to do subsystems. Let's do signal generation, and we'll do signal generator here. Okay, what I'll do is this. Okay, we'll have fundamental frequency. So I might test this over 10 frequencies, so to speak. Okay, 10 frequencies. So this is the fundamental frequency. Okay, and what do I need to do? I'll go and look inside. I will use I will say the signal type can be determined via terminal, amplitude also via terminal, offset via terminal, and frequency via terminal. Okay, I'm not gonna save. Okay, so the frequency, I can create a control. Okay, and I'll type fundamental frequency. Okay, maybe I'll just put a hertz thing over here. And then I can make a control. I'll put the amplitude. And what else? I'll make a control for the offset. Offset. Okay, and the last one will be waveform type, signal type. I'll make a control for that. This is an enumerated variable, signal type. Okay, so I'll just leave it as it is. If you go to the front diagram, that will be here. Of course, you can actually wire this in. So 1, 2, 3, and the signal type will be sine. 4. Okay, so I will do this. Yeah, I will do this. It will. Oh shucks! Did I just close everything? Oh, I did. Let's see how much I actually saved. Yeah. Okay, everything is saved. Okay, so yeah. Basically, it'll be like this. However, I'm going to make many copies of this waveform generator. So let's make a constant. Oh, we're going to make an indicator here. This is the output. So the output can actually go here. So we'll call this the output summation of waveforms. Okay, so that's all this is doing. Now, what are we going to do? Okay, I'm going to copy and paste this VI over several times. Okay, and what am I going to do? I'm going to keep everything the same, except I'll change the fundamental frequency. So let's say, how are we going to plan this? Okay, let's say I want one at my fundamental frequency is 1 times 10 to the minus 3 hertz. I want something at 2 times 10 to the minus 3 hertz, 3 times 10 to the minus 3 hertz, and go all the way up to 9e minus 3. Okay, and I'll go 1 times 10 to the minus 2, and you go all the way up to 9e minus 2, 1 times 10 to the minus 1, and you go all the way up to 1 hertz. So I want 10 data sets. Okay, 10 frequencies, sorry. 10 frequencies in each range. Here another 10 frequencies. And last one, yeah, another 10 frequencies. Okay. And what is this called? This is called broadband. We call it broadband. Why is it called broadband? It's because there's more than one frequency. Okay, so you don't just have one single frequency. You have a band of frequencies that you want to test. Okay, so if you know your internet, in your internet has this. It used to have this thing called broadband. Before 4G and everything came about, there was this thing called broadband, and at one time it was the fastest internet. What is broadband about? It means that you can transmit data across several frequencies. So that's an electrical signal you're transmitting, or electromagnetic wave if you think about Wi-Fi. But it means that you can transmit signals across many frequencies. So if we have a dual band or dual frequency, okay, sometimes your Wi-Fi has 2.4 gigahertz, 5 gigahertz. That means you can transmit signals across two frequencies. But anyway, that's I get myself carried away. But yeah, this is what is broadband. This is what broadband means, because you can test multiple frequencies at one go. So that's what we're going to try and do. Oopsie. So 1 times 10 to the minus 3, 2, 3, 4, all the way up to 9. So I need if this is my fundamental frequency, I need to times 2, times 3, and then all the way to times 9. Right? And likewise, if I do this, I need a times 10, times 11, all the way to, times 10, times 20, and then this one is times 90. Okay, and over here it will be times 100, and you go all the way up to times okay, this is times 1000. So this is maybe 11 frequencies, not 10. So that's the plan here. Okay, so I'm going to have a multiply. So I'll make a constant. I'll say I will have a times 2. Okay, 2 times frequency. Okay, so I'll take the fundamental frequency, I'll multiply that by 2, and that will be the frequency. Okay, there's in simulation subsystems you cannot really use local variables, so too bad. But this is what we'll do. Okay, we'll wire things up as such, and the offset will be at the bottom. Okay, signal type will be the same, and then instead of having just one signal, I will have two. So this is a summation of waveforms. I'll use compound arithmetic, and then I'll just plus them together as such. Okay, so now I have two sine waves. Okay, and I can do this, I can repeat this as many times as I want, but I'm not going to show that in this video. Okay, what I will do instead is I will try to make a new VI, and then I'll try putting this through. Okay, so let's try this in a new VI. And I'm going to edit the icon a little bit. Or maybe I'll do it later. Artistic work can wait. Okay, so yeah, I have this, and let's test it out in a VI and see whether it works. Let's see. Oh, cancel, don't save. Alright, so this is the summation signals VI. Okay, and let's make a new VI. And I'll save this as let's put it in dependencies up here. You put it here. Testing summation frequencies VI. Okay, so very simple here. All I'm going to do is just one control and simulation loop. One simulation loop. Yeah, control and simulation loop. Okay. Okay, for this, very simple. We're going to set the timing here, have a non-nan infinity check, final times infinity, synchronized timing loop, and we'll use Wrangler kata 1, click OK. And let's put our new VI in. So right click, select a VI, go to dependencies and put summation signals right here. So later on then we are going to put this VI in here, but now it's just like a testing phase. Okay, we are just going to test it because this thing is still running. We still want to test data. We are running a square wave, but here we have a summation of frequency. So I want to see what that's like. Okay, so let's try. So this is the signal type. I'm going to create an indicator. Oh no, not indicator. I'm going to create a control for that. Control for signal type, a control for offset. Okay, I'm going to have a control for amplitude and a control for the frequency, the fundamental frequency. And now of course outside I want a waveform. I'm going to use the waveform graph utility. Okay, so that's what it will look like. So let's go to the front panel and let's see what we can play with. Okay, so fundamental frequency 0.5 Hertz. Signal type will first be sine, but I want to try and test other kinds as well to see whether it works. Oh, wow, this is slow. Yeah, this is very slow. I think what's going on is that yeah, this thing is still calculating. Oh, it's almost at 20 minutes. So yeah, actually this thing needs to run, I think. Yeah, let's see. Oh, this thing is very slow. Okay. Yeah, this is a square wave. This is a square wave. That's why. Yeah, we'll let it run a little bit longer. Yeah, but the reason why this is slow is because the LabView is also running the other programs simultaneously. So this thing kind of has less resources. Now you can see that the sine wave is working. There's a summation of sine wave. It almost looks like a sawtooth. Yeah? Sawtooth wavelength. Sawtooth waveform. Okay. Now let's try a different signal type. Maybe let's instead of sine, I'll use a square wave. Alright. Let's play. Okay, so we have that. It's like it will be oscillating between 1 and yeah, I'll be oscillating between 2 and -2 for some reason. Yeah. So if we have this square wave waveform, this is what will result. I know it doesn't look so nice now because I'm still running tests for this one, the square wave. The square wave bits. Okay, I think we're about 1,000 seconds now. I think I can stop. Okay. So I think the other, I can stop and run again. Wow, what's going on? Okay, let's see. Auto period. Oh, I forgot to auto period this thing. Now, okay. Ah, okay. This is much smoother. Okay, forgot to auto period. Maybe it's the auto period was the thing. So it's running 10 times slower. Okay. So that's the square wave. Sawtooth is like this. You can change to random noise as well. Okay. Yeah, random is very hard to make out what's going on, so I'm not going to use that. But as you can see what I'm trying to do here is to have many signals to sum together at the same time. Now before we end the video, okay, let's do some let's do some analysis on our square wave file. Because we just finished this test, and let's try to run a square wave. Wow, 35 minutes. Okay, I think I'll stop. And now I will do this analysis in the next video. Okay, I'll see you again.